think I can begin.
Just 1 minute.
Oh, 1 more minute. Okay.
So I'm glad to introduce our next speaker, Jordan Keller from Dynamical Initiative at Harvard. And he's going to speak on BMS past and future development.
So thanks very much to the organizers for the invitation. It's great to be back in Taiwan. So in this first talk, I'm mostly going to be discussing the Bms Algebra, some background on it. I guess Yekai talked about it just a few hours ago, and this will be a somewhat different perspective on it that I'll present. So the setup is we have a space-time given in Bondi-Sachs gauge, or with these Bondi-Sachs coordinate conditions. And let me just remind you of what those are. So we ought to have u is equal to constant being null hypersurfaces. In other words, expressed contravariately, GUU should vanish. We have these angular coordinates. XA, and the trick was that we sort of parameterized a surface and then propagated along the null cone given by u is equal to constant. And the way that works out contravariantly for the inverse metric is vanishing of these cross terms. And then finally, our radial coordinate R has some normalization. So it sort of serves as an aerial coordinate for these surfaces such that determinant of GAB, determinant of GAB, determinant of this surface metric is what one would find same as the standard round metric, scaled by r to the fourth. Okay, I guess you guys have been using sigma tilde. Okay, so covariantly, we have vanishing of these three components. Remember, A is indexed like A is equal to 1, A is equal to 2. And we have finally this determinate condition. So we have 4 conditions. We don't have any remaining gauge freedom. And the metric, as a consequence, the metric takes the form like so. Yeah, and I apologize, I'm using a slightly different normalization as that employed by Yikai and by Muda, and by Poning. So I guess they use some V over R in place of my V. They use e to the 2 beta rather than my u, and then they sort of pull out an r squared from this metric sigma and call it h.
Your G is the same as your sigma.
Sure, I guess this is sigma AB. Yeah, sure, the AB component of G is just sigma. Yeah, so the determinate condition is so we have 6 degrees of freedom. We have the symmetric tensor, 2 tensor on the surface. We have 2 scalar functions, uv, and then we have a covector, w. And that's sort of 7 variables, but at last we have this final condition on this surface metric, this 2 tensor. So we get down to 6 degrees of freedom. And from our perspective, we can draw some Carter-Penrose diagram of the space-time after performing one of these conformal compactifications that Yeka has told us about. We have our scribe plus, and it's sort of thought of as r is equal to infinity. And it's sort of where we are the observers. If we're thinking about one of these sort of isolated system setups that Buta told us about, where there's some central object and infinitely far away, here we sit. Here's, say, a constant u null hypersurface. And in this direction, we have this increasing u. And so what we want to do is we want to impose Einstein's equations, and we end up getting a set of hypersurface equations on this constant u null hypersurface. We end up getting some dynamical equations along null infinity. And sort of by looking first at the hypersurface equations, we'll be able to integrate them term by term away from null infinity and find some sort of observables. And then we'll be able to track the dynamics of those observables along null infinity using the evolution equations. So this has all already been covered, just to review. So I'll try to get through it in short order. Do I want to? I'll just erase it. All right, so we've imposed this gauge condition on our smooth manifold. And now let's impose Einstein's equations as well. Sorry, just to remind you, this is the Ricci tensor. This is the scalar curvature. Together they make up the Einstein tensor, and this is the stress energy tensor, which sort of encodes other physical phenomena besides gravitation. And for us, we'll just sort of assume that there are no other phenomena and just focus on the vacuum case. In other words, we're talking about a Ricci flat 4-manifold. So we want to take want to examine the Einstein's equations, and sort of look at them in powers of 1 over r. So let's see. It turns out that we need only focus on two sets of equations. So we have these hypersurface equations. EUA is equal to 0, where A is any sort of space-time index. And then we have these dynamical equations, just like so. Oh, yeah, it is. It is. I've already contracted with those indices. That's right.
Your E and G should be switched inside the parentheses.
My E and G should be switched inside the parentheses. I should lower indices or something?
No, you didn't. Well, I mean, you did define E after.
Oh, okay, sure. Yeah, sure. Sure, I can contract over that. That's fine. And so, as I mentioned, these guys here give you sort of a radial ODEs on the null hypersurface, and these guys here give us dynamical equations along Scri plus. Okay. Yeah, these are the evolution equations. This is all just following Madler-Winnicor, and I believe Mutau has said everything that I'm saying. So just for example, so these hypersurface equations, these are radial ODEs on U is equal to U0, this null hypersurface. To give an example, we look at EUU, we end up getting the following ODE. So not the most beautiful thing you might have seen, but it is what it is. What did I use? Yeah, I did, okay. And it's almost done. So assuming we had knowledge of U and of WA, we could sort of integrate to find V, assuming we could treat them as source terms. And I guess we also need knowledge of sigma, given that we have its scalar curvature over here. And the way it was set up was there was sort of a hierarchy. So just to remind you of the thing that Mutau discussed, the way it begins is we have some determinate condition on sigma, and we sort of get an expansion for it. And we see that the shear tensor pops out. Next, if we look at EUR is equal to 0, we find some ODE in U with right-hand side, say, some function h of sigma. So we've already understood sigma via our determinate condition. We can plug it in here and integrate for U. Looking next at EUA, we get an ODE for this cross term, say, call it M. And at last, inserting all of them into the original equation I just wrote down, the example, if we knew sigma, we knew U, and we knew WA, we could sort of integrate to get an expansion for a V. When I say integrate, we have these radial ODEs. We're integrating from null infinity, assuming some expansion in sort of inverse integral powers of 1 over R. And just to give that expansion explicitly, we have, well, we already wrote sigma on the other board. So remember that this is the shear tensor. It's a symmetric traceless two tensor on these surfaces. U has the form so again, we looked at its ODE, and from knowledge of the expansion for sigma, we integrated, and obviously the dependence of it is simply upon the shear tensor. For W, we find, well, again, there's some dependence on the shear tensor, but there's actually sort of a constant of integration of sorts that appears at the next order. We have to introduce some new piece of data, just call it LA. I think Poning used some similar notation. This is sort of our angular momentum aspect covector. And then at last, we look at the ODE for V. And given the knowledge of these expansions, integrate, and we find V is equal to 1 less. And again, an integration constant appears. But at the next order, we find something that really just depends upon sort of these quantities, this data that we've introduced so far. So overall, the metric expansion, the expansion of the metric components, the expansion of the metric components reveals sort of a shear tensor, this angular momentum aspect, and finally, this mass aspect function. These all appear sort of at pretty high order. And so for us as observers at infinity, they're sort of what we're going to see and what we're going to work with to make measurements about the space-time or to understand it. Oh, do I mean W lower A? I think it's.
Your notation on the right.
Oh, I see. I don't think I think that I want it to be. Well, I guess let's see. There would be a factor of R squared. Either way. Let's see. The vector should be of order 1 over R squared, right? Yeah, I think so, right? Because the metric expansion eventually looks like. And that more or less gels with this being 1 over R squared, contract with something that's R squared. Yeah, so I think that's, yeah, but thanks for pointing that out. Wasn't being consistent. So if we actually write these in, these expansions for U, for V, for sigma, and for W, in terms of these quantities that we've introduced, we have an expansion for the metric and powers of 1 over R. Governed by these 3 pieces of data. And so the metric at the top order is just the Minkowski metric. Then we introduce some sort of Schwarzschildian part. I guess I'd finally say that there's some Kerr-like piece. Kind of writing things out of order. And then we have all the rest. Where this shear tensor comes into the picture. Yeah, and it turns out that for these sort of very explicit stationary spacetimes that we talked about, the Minkowski, the Schwarzschild, and the Kerr, you can always sort of cook it up in such a way that this shear tensor doesn't really play too much of a role. So that's why I write it, and it's the terms involving it last. So the metric in terms of the mass aspect, the angular momentum aspect. Oh, I guess I'm using L and the shear tensor. And remember that, I guess this is differing by some multiple, but we also have this coming from the shear tensor, this news tensor, NAB. And I'll just call it the U derivative. The U derivative of the shear. It encodes in some way gravitational radiation. You might remember it showing up in this formula for mass loss, the mass radiated away from one time to another. And again, this sort of explains why we can sort of minimize its role in these stationary spacetimes like Minkowski or Schwarzschild or Kerr. Doesn't really appear. So if we wanted to, at this point, we could.
You're using that's lower index, that's upper index, and you're lower up. You're using sigma divided by r squared, is that right?
I'm using sigma, which
sigma to lower and.
Oh yeah, I guess I'm always using. I guess you'd have to actually use the actual surface metric sigma to raise and lower indices. I don't think I'm.
Therefore, your upper and lower index divided by r squared. Right?
Yes. Yeah. They should. So, for example, here, that's why I was doing this quick count to see whether r squared was the appropriate order to begin at.
Expansion. Yeah. So that's why in this expansion, right? LA corresponds to 1 over r.
1 over r squared of this gadget here,
right.
of the vector.
Right.
I guess I shouldn't have called this the aspect covector either. It should just be the vector. Right. Yeah. But anyway, these are kind of, you can move between them pretty easily by raising and lowering indices.
And the divergence of C term corresponds to 1 over r squared of W.
That's right. So it corresponds to this contraction. So this is of order r squared. This is of order 1 over r squared. And you wind up with something constant order right here. And so we have, for us as observers, we can just focus on these quantities and also the news tensor and sort of understand the metric and the spacetime in terms of these. So these are sort of what we're going to make measurements with. For example, this Troutman-Bondi mass that we've been talking about. And if we wanted to, at this point, we could sort of track their evolution by looking at the remaining Einstein equations. Remember, we just have integrated these so far and sort of defining these observables. But that's not something we're gonna move on with. What I wanted to talk about was we use these physical observables that is to say, use this sort of Bondi-Sachs data really the news, to make measurements. E.g., the bonding mass, for a particular section at null infinity, particular cross section, take some surface, integrate the mass aspect function over it, we find this bonding mass. I mean, the question is, where does this formula come from? We have these different observables, and we want to sort of formalize some process by which we can make measurements. So where did this Troutman bonding mass formula come from? The other thing that we might be interested in is, well, we have this spacetime and we imposed a Bondi-Sachs coordinate system on it. That might not be the only Bondi-Sachs coordinate system that exists for this spacetime. There might be all sorts of ambiguity to it. And if there's another Bondi-Sachs coordinate system, there's going to be new data. And so we might wonder, I made a measurement of the Troutman bonding mass in one Bondi-Sachs coordinate system, and I could make it in another coordinate system, and how do I know that these things agree? So how do I know this is a physically meaningful measurement? It's not just dependent upon, not so much the observer, but I guess the choice of Bondi-Sachs coordinate system, given that there are a multitude of them that preserve this sort of asymptotic structure that we have here. So it turns out that the answer to both questions is to get a handle on this sort of ambiguity in the Bondi-Sachs coordinate system, and we wind up figuring out that there's some sort of class of asymptotic isometries or asymptotic killing vector fields that exist for these spacetimes. So let's see. I want to understand sort of the origin of these. And we haven't really discussed so much the Bondi-Sachs group. I guess I'm going to talk more about its sort of related algebra. So let's sort of recall. The definition of a symmetry. So we're interested in asymptotic killing vector fields. What is a killing vector field? Well, we have this killing equation, right, which works out to being in local coordinates. Let's see, do I have space to write this? I probably don't. We're interested in vector fields X, which gives some sort of infinitesimal isometry, which does nothing to the metric. In other words, we're interested in X that satisfy the following equation in local coordinates. And so you can imagine imposing this with the Bondi-Sachs coordinate system. Okay. Now, for example, we could consider the Minkowski spacetime. Where the metric has the form and as has been discussed several times, there are all sorts of Killing vector fields, and writing down a basis for such, well, you have the time translation and the spatial translations, and you also have the rotations, and finally the boosts. So some 10-dimensional set of symmetries of Killing vector fields that satisfy the following. If you look at Schwarzschild or Kerr, well, sort of the number reduces. So Schwarzschild just has this dt, and it has these rotations. And Kerr is even worse. It just has this dt, and say this rotation, well, if I fix an axis of rotation as, say, the z-axis, then it would just have the following rotation vector field. And for general spacetime, you're not going to have any Killing vector fields. But what we could hope for is we could hope for something that satisfies Killing's equation, maybe sort of in powers of r at higher order. So it preserves the metric at higher order, and maybe later on things start to go a little bit awry. So not exactly a Killing vector field, but asymptotically so. So what we're looking for is yeah, so in other words, when we take G plus this deformation along the vector field x, we want this thing to preserve this Bondi-Sachs form here. Okay, we want it to have roughly the same expansion. So let me just give some example with the super translations. Let's assume some growth behavior for the vector field's components, just like so. And when we actually take a look at the deformation equations as given by this formula, it turns out that looking in the GRR component, we get like so. And remember that in the Bondi-Sachs gauge, this component ought to vanish. So when we tack something onto it, again, ultimately, we should get 0. In other words, x of u, this component, should be radially independent. And likewise, when we shift over the UR component, what we find is sort of a higher order term like so, and then lower order contributions. Now, the point is that over here we want to have a leading order term of du dr, which is just -1, right? And in that case, we sort of can't add anything to it here. We need to have, in other words, both of the following being true. Okay, from these two equations. So in other words, this u component should just be a function of the angular variables. And if we go and look at, well, if we assume now sort of a expansion for x, that's using these asymptotic conditions on the components that we've assumed and using also this information we derived about the u component, then x looks just like so. And if we go and compute these remaining deformation components, what we find is the following. Yeah, sorry, this is a little bit involved. First is like so. Second is like so. And finally, the angular component looks like so. And if we look at these here, so again, we've sort of removed the R dependence from these guys here. These are, just want to emphasize, the fact that we're expecting ultimately leading order behavior like minus du squared plus 2m over r du squared, etc., out of the du squared term, tells us that that this guy here ought to be independent of u again. And when we actually go to, go to solve for it from here, oh geez, I'm actually out of order. What do I want to say? Oh, sorry, what I want to say is this. The gauge condition GRA is equal to 0 has to be preserved, and so from that immediately we get the expression for this first angular term in the vector field. And looking at the next order term, again, we need to preserve this so we can find next order as well. And putting this expression here into the linear order term of the deformation of the surface metric, well, one thing that we do know about this is it should look like a shear tensor. This is sort of our new shear. In particular, it should be traceless. So when I take a trace over it, well, the trace of the news should vanish. And here we end up getting sort of a divergence. So what we find in the end is x of r0 looks like 1/2 lambda f. And I believe there's a little bit of a possibility that it could have some additional, I guess could it have any additional u dependence? I don't think it can though because of this equation somehow or other. Let's see. I don't actually think we even need to use that fact though. I think we can just see that it has no u dependence directly by taking trace like right here. So actually we can also solve at this next order now that we have expansions for the two angular terms and the first expansion of the radial term. We can finally solve for R1 as well. I think using it and the next order here. So this is, again, something involving XR. So XR2, XR1, the next order, the radial component, and all the things that have preceded it, which we've solved for, we can actually finally solve for this next order term. And it looks just like this. And so this is just the expansion for the first couple of terms for an asymptotic symmetry, which preserves this Bondi-Sachs metric structure for the space-time. And we can actually create one of these things for any choice of f, where f is just a function on the surface. So I guess it's a different way to write down on the physical space-time, in sort of an asymptotic sense, to write down the vector fields that Yekai was discussing in his talk just a few hours ago. I guess it looks quite different though. As I say, parameterized by this function on the surface. And actually, it's a little confusing to me. I don't actually know, is there a straightforward way to go from this vector field on your physical space-time and see how it's pulled back by this mapping? This, I'm saying that we have this scry. And this, what do you call them? What are these extensions called? Yeah. You're conformally compactifying, but what do you actually call it? Yeah. An asymptote. Yeah. Can you actually? I don't actually see how this vector field in the physical space-time relates to the super translations that you wrote down here. I just sort of know this physicist method of writing them down from Strominger's book.
You wrote this in alpha. That's the alpha and the bar.
That's the first term.
That's the first term.
It's like this, yeah, but then the point is that things really, oh, this should be dr, sorry. This is the thing I am a little confused about. The fact that there's a transversal term or something like this is a little weird. So it's not perfectly tangential to I, and so it shouldn't be so straightforward to push it forward along the inverse of this diffeomorphism. So it's a little strange, but for example,
The part of the dr in photo you're not going to see,
But it's not tangential, so the vectors cannot be vectors.
yeah, because you really take the inverse of it and you just push forward the tangent space, the vectors in the tangent space using that map. That's what's going on. You can't do the transversal vectors. But on the other hand, I mean, just to have some sanity check, if you just examine the translations, one thing you could do is you could simply write down the spatial coordinate xi as r times this first eigenfunction. And this is sort of relating these two coordinate systems, sort of a standard Minkowskian type thing with the Bondi-Sachs. And just taking exterior derivatives, you've got the following. And if you raise indices, well, you get the translation here. And I believe that you just get something that looks a lot like this with f taken to be. Taken to be this first eigenfunction. In other words, something that has a radial component. So something that isn't just tangential to this extra thing that you've tacked on. I believe that would actually pan out that calculation. So this was a huge surprise for Bondi-Sachs and Vanderberg and Metzger and all these people working on this. I think that their expectation was that, yeah, you only really care about preserving the metric structure at the top order. In other words, you're only interested in preserving the Minkowski spacetime, more or less. And so their expectation was that you would just find the Poincare algebra. But you've sort of got this enlargement. So you've enlarged the translation subgroup. Pardon? I would say so, yeah. In the way I'm deriving it, it's just in terms of these vector fields are only sort of killing exactly at r is equal to infinity. And as you go away from r is equal to infinity, so as you're away from null infinity, they immediately stop being actual symmetries. So, yeah. And in terms of the original motivation for this, in terms of making measurements for observers at null infinity, it seems like Yekai almost wrote down in this Garrosh paper sort of what you would do with this. You could imagine just taking a function f. Think about it just as some L2 function on the sphere. And, sort of just counting, integrating against the mass aspect function and getting an infinite number of measurements. say if you chose some L2 basis on the sphere. So take a bunch of harmonic polynomials and multiply them by the mass aspect and make a bunch of measurements. You get a much better sense for the mass aspect compared with just computing the Bondi-Troutman mass. Okay, so let's talk about this sort of speculative enlargement that the physics people have been getting excited about the past couple of years. So there's also sort of this notion of super rotations. At null infinity. So we have, let's sort of begin with an ansatz for our vector field. Let's assume the vector field takes the following form. And by the way, if we talked about these rotations or these boosts from earlier, they were written in terms of the standard coordinate system. If we made a coordinate change into sort of these Bondi-Sachs type coordinates, this is exactly how they would look. Where we're talking about y is one of these conformal killing vector fields on the unit sphere. Particularly, you could think about ya as being the gradient of this first eigenfunction. These would correspond to the boosts that we wrote down earlier. Or we might consider something that looks rather rotation-like with these written in terms of these first eigenfunctions. And yeah, this corresponds to these rotations from earlier in sort of these Euclidean coordinates, t, x tilde, x sub I. So, right, we take one of these conformal killing vector fields on S2, write out some expression, and this is what we find. But let's just consider now something more general, where we haven't specified ya. So now y is just some vector field on the sphere. If we go and do this analysis of this infinitesimal perturbation, with an eye towards preserving the Bondi-Sachs structure of the metric, it turns out that every component does what we want. These guys are all good without any specification of ya. We don't need it to be a conformal killing vector field on the surface. So for these components. Now the fly in the ointment is the final component, namely the deformation of the surface metric part of it, which looks like so. Yeah, sorry, I have not been super careful about the connection I'm using. I guess it doesn't matter since this is just a conformal killing vector, conformal killing equation. So it actually doesn't matter so much which connection I'm using, or which geometry. But yeah, I've been meaning to use the round connection all along. Oh, I guess this is just a bunch of nonsense right here. Well, it's not such nonsense, but right. So what I want to draw your attention to is this top order term. So we've already got in GAB, this guy's already got this top order as the flat metric. And now we're adding something to it. This better vanish, basically, because we need this total object to preserve the Bondi-Sachs expansion structure. So any sort of R squared that we're adding, that's not good. We've already got what we want at the top order. So we need this to vanish. In other words, we do finally at last need to have this CKV equation. And so we have these globally defined conformal killing vectors. Now the thing that physics people are getting excited about in the last maybe 5-10 years is just the notion that
why were the conformal killing field the ordinary and the general vector field, that's a case of superrotation.
Not quite. Yeah. So yeah, the thing they're getting excited about is not quite a general vector field, although some people like Strominger do favor that, and which doesn't make any sense to me. Yes. So there's two proposals on the table. So one group of physicists say, take any old YA, it's just any sort of smooth vector field in S2. And that doesn't make much sense to me because I don't see how you're preserving this asymptotic structure of the metric, or of the Bondi-Sachs. You're not preserving the Bondi-Sachs structure. So it's just some real smooth vector field on S2. The other proposal, which I like a lot, is what about Y as some local conformal killing vector field? So it's something that satisfies this equation, but it might not be globally well defined. And just to give you some parameterization for that, what if we take some complex stereographic coordinate, say z is equal to e to the, taking the usual theta and phi, take z as the following with some polar angle like the azimuth and then some radius given by the cotangent of the polar. And what you find is that g looks like so. And for a vector field, written in these complex coordinates, from what I'm aware, the condition couldn't be sort of simpler. You just want to have something like this in order to satisfy the conformal killing equation locally. Yeah, let's see, I think I wrote that right. So, in other words, you could take some basis like so, and you would have an infinite family of vector fields which satisfy the conformal killing vector, conformal killing equation. In particular, if you look at lower tier integer values for n, and you take some complex combinations, what you end up recovering are the global CKVs. And I'm not sure whether Bondi, Sachs, et al. Were aware of this when they derived the algebra. It could be that they knew about this fact and just discarded the non-globally defined vector fields. But for the physics people, I mean, the philosophy is anytime you get some sort of enlargement of the algebra, you've got more measurements you can take. If you have more y's, one way to measure angular momentum one possible way is to take the angular momentum aspect and to integrate it against this y. Well, yeah, having more different ways to do that is better than not. On the other hand, you've got some real problems in terms of, well, for one thing, we've been talking about a vector field algebra so far, but all these things can be integrated, and the super translations, for example, have an associated diffeomorphism, so we can actually write down sort of the nonlinear transformation as well. To my knowledge, these super rotations have not been integrated in this way. I don't think anyone's been successful in sort of writing down a diffeomorphism associated with them. So sort of a group element associated with this algebra element. It's a little bit trickier to exponentiate as far as I'm aware. The other thing, sorry.
So this, well, then you could talk about super translation. Just by plotting some f that is not even globally defined on x2. Right?
Yeah, you could. So I think the best thing to do is to take f is equal to delta of p on the surface, and then you say, for example, they have this conjecture that whether the mass aspect is pointwise positive, not just the Bondi mass. These physics people say, oh, I can measure it at any angle now because I have the super translations. But they don't care about regularity. Yeah, that's the other thing I was going to say was, so now we have these super trans, which we're thinking about as, I mean, I sort of think about these things as having some regularity, say like so. But when we make this enlargement and we have super rotations, I believe this algebra has this sort of twisted structure whereby we need to make sure the algebra is closed. We've introduced these new vector fields y, so schematically we're going to end up feeding new things in to the super translations. And what happens is you end up getting sort of way rougher super translations that you need to add. You need to sort of, it kills all this regularity that you had on the super translation function originally to maintain closure of the algebra.
I guess that one makes up. I mean, when you take f, for those that correspond to actual translation, they sit in the lowest mode.
Yeah.
So they have this. You can write it down as this is easy bar.
Yeah.
You can go a little different direction. You can require that L come from some holomorphic object, but not necessarily regular.
L comes from that? What do you mean L? You're talking about
F.
Uh-huh.
So before when you upgrade f, is that you go from the first eigenfunctions.
Yeah.
Upgrade any general functions.
Right.
But what I mean is I can upgrade from first eigenfunctions to any kind of holomorphic functions.
You could also complexify it. Yeah. Yeah.
It doesn't have to be holomorphic.
Yeah.
Meromorphic functions.
There's no restriction on f whatsoever in the super translation. It's just some angular function. I guess it doesn't even have to be real. But in any case, I think a lot of people just thought about it as doing something like this. And the problem is when you add these guys to maintain the closure of the bracket, you have to end up adding so much stuff. It ends up becoming quite wild. So the reason that so there are some real serious difficulties with this extension to include these super rotations, but the physics people are really pretty committed to it and pretty interested in it. And I think the reason for that is that they have these sort of ADS-CFT correspondences, and somehow this sort of Virasoro, what they call this sort of Virasoro algebra that appears in the super rotations and this augmentation of the ordinary Lorentz algebra factors heavily into ADS CFT, and they've sort of made it work to great effect using boundary data to understand the space-time. Oh, they say it's 2 copies of the Witt algebra. So just to conclude, we now have a plethora of asymptotic symmetries at null infinity for these Bondi-Sachs spacetimes. We mentioned that there's some way to use these symmetries to actually write down measurements. In particular, some way to motivate, for example, the Bondi-Troutman mass that's been discussed. So let me just kind of hint at this relationship. So if you had a conserved, that is to say divergence-free, stress energy tensor on some background spacetime, so say TAB is some conserved stress energy tensor on the same old background we've been working with so far, and if you had a Killing vector field, then what you can do is you can form a current. Let me call it, I guess, J. And the thing about the current is it's divergence-free. As TAB is conserved, and as K satisfies the Killing equation, so J is conserved. Oh, and I guess I'm using symmetry of the stress energy tensor in deriving this. All right, so the stress energy tensor is assumed to be divergence-free. It's also assumed to be symmetric, so we could always symmetrize this. And yeah, I apologize. This is just Killing's equation in disguise. You could write it down as or like so. So, in other words, if we have some space like hypersurface, say with some normal vector eta, well, we could form a quantity like so. Well, I guess I should say some foliation. And Q would be preserved from one moment to the next. So let me just try to make this a little concrete. If, for example, we had a fixed space-time background and we had some scalar field. Say on Care. Seeing as Care has this global symmetry dt. So if we had a scalar field which satisfied the wave equation, then it's got some associated stress energy tensor. Then from what I've just told you, we ought to get some conserved energy, right? We have a divergence-free stress energy. I think it's something like this. And then we apply the wave equation. Of course, we have this dt, which I mentioned satisfies Killing's equation. And so in other words, if we had some sort of some time 0 and some time 1 encoded by some hypersurfaces, because in the region between them the current vanishes, then what we find is some conservation law. So not only do we have sort of a natural way to define charges in the case where we have a Killing vector field K, but we even have conservation thereof. And things are definitely trickier at null infinity. It turns out that conservation kind of goes out the window. We've already talked about the fact that there's gravitational radiation and this Bondi mass loss formula. On the other hand, there is some hope of constructing some charges. We do have the Bondi mass. And it, for example, basically comes from the time translation symmetry, part of the super translations. And then the hope is to get something like, well, spatial translations ought to give you linear momentum, and then finally, ordinary rotations and boosts ought to hopefully give you some notion of center of mass and an angular momentum. Yeah, so let me write that down somewhere. Yeah, there's more difficulties in GR. There's not some sort of straightforward. Stress energy tensor. The other issue is that we don't really have symmetries. We have approximate symmetries. And then sort of the result is that we wind up with, well, not quite conserved quantities. And the rough outline of what one would hope for is we have a symmetry and an associated conserved quantity. Well, we have dt and di, the time translation, spatial translations. These here are like mass and linear momentum. We have the rotations. hope for some measurement of angular momentum for the system. And finally, we have boosts. And we hope that they give us some measurement for center of mass. And it turns out that well, there's different kind of settings where it's possible to make these measurements in GR. For example, at spatial infinity, there's a pretty successful theory for doing this in the ADM formalism, and we have all these ADM quantities that work out quite nicely. And in fact, they are conserved. And there's even some kind of notion of measuring them quasi-locally for surfaces in the space-time that are away from these asymptotic regimes. And so for these sort of surfaces that are in the bulk of the space-time, that are away from spatial infinity or away from null infinity, it doesn't feel like there's any hope of measuring these things because you're very, very far away from having any asymptotic symmetries. You're not way out in infinity where you're approximately Minkowski. You really are in the dead center of the space-time, where your metric is quite far away from those things. But nonetheless, there is some sort of notion due to Mudau, to Yao, and to Puning of measuring these things quasi-locally. And then finally, in recent years, there's been some sort of attempts of doing these, and then also of extending to super translations and super rotations at null infinity. And I guess that's what I'll talk about next time. This sort of attempt by Wald, he sort of made the first attempt in the late 90s, and then by some other people to put this on a firm footing at null infinity. But I think I'm actually out of, I didn't expect to get so far so fast here.
Super translation and rotation exists only at infinity. Your prescription of getting a conserved current requires a vector field that exists everywhere. Right?
Mm-hmm.
So how do you do that?
So
And besides, your t is equal to 0.
you're talking about this schematic right here?
In the boundary stack metric,
Uh-huh.
your t is equal to 0. So
In the bodies?
you construct j equal to t and
Oh, that's what I meant to say when I talk about difficulties in GR. There is no stress energy in GR. You can't just follow this procedure. This is sort of purely kind of Lagrangian in a way. We haven't, the way that these things are actually constructed in GR, given that you lack a stress energy tensor, is you use some sort of Hamiltonian formalism, and it's totally different. I just meant to present this to give you some schematic for how things might go. In GR, it's a different ballgame.
another question is that the local conformal Killing vector field form analytic algebra.
Mm-hmm.
Is there a way to see a central extension from gravity?
Yeah, what people do is you have this subalgebra of superrotations, and what you try to do is you try to cook up in this Hamiltonian formalism some integrals associated with them, some measurements. They try to construct some sort of charge algebra. And just as you say, when you actually take this charge algebra and you write down some central extension of it, kind of the weird thing is they end up getting measurements for the black hole out of it. That's what they're really excited about, are these central extensions that you mentioned. So for example, Strominger and some collaborators of his, I think the same crew, Hawking, Perry, and Sasha Heiko, they just constructed some central extension in Kerr that allowed them to compute some entropy for Kerr that they wanted. But it somehow, you don't centrally extend the algebra of vector fields, you extend the charge algebra, and that's one other motivation for them for actually writing down these charges. They don't actually care that much about the measurements.
Are the charges the usual Norton charges, or they are not?
I don't think they are. The thing is that
So these one are not supposed to be the symmetry of the usual sense.
I think the point is that when you write down the Noether charge, you hope that it gives you some sort of integrable Hamiltonian, but it doesn't at null infinity. And what you have to do is you have to. It's because there's radiation. If you didn't have any radiation, things would be fine, and the Noether charge would be usable. So if your news vanished, you'd be able to use these things. But what they end up having to do is they end up having to add some sort of correction term. So Wald proposed some correction term that I'll talk about, and there's almost like a cottage industry of just proposing some correction to the Noether to get what you want in the central extension. So in this paper, for example, I think they make some proposal to get them the answer they want. But it's kind of a wilderness, though.
Okay, but what is the principle that makes it possible to claim that these are the charges of that algebra?
Well, you need to, they want to derive it from a Hamiltonian formalism, but you need to make some correction to the obvious thing, and it seems like all sorts of people make all sorts of corrections to give them the final answer that they want. It doesn't seem like there's any well-defined scheme for doing so at this point. That's, especially for the superrotations, why things are kind of up in the air at this moment.
No, any other question? Actually, did they ever talk about, this kind of hidden symmetry, like Killing-Young tensor, at this point?
I never know. And actually,
But presumably you can just write down equation just like this Killing field, right? Asymptotic Killing field.
the same thing should be true for the
Yeah,
conformal. There should also be conformal killing vectors, approximate conformal killing vectors. Like Minkowski has a.
This Killing-Young,
Yeah. Oh, you're talking about this. It's also one form. You're not talking about the Carter.
No, I'm talking about this kind of two tensors.
Is it two form?
Or
Two form.
Killing-Young.
Yeah. This thing that contains everything.
Yeah, I mean, though, but there, I mean, presumably if you take two Killing field and you take the tensor product, you can get one of them. But in some of the, like for example, in Kerr space, and you do have those irreducible, right?
The Carter tensor. Yeah. Right. I actually never heard of this. No, I never heard that they thought about this. About what. But surely, because the thing is Minkowski plus more, surely the Carter tensor would just be. I mean, in Minkowski it's reducible.
What's interesting is whether you actually have some irreducible one. I mean, in the case of Minkowski, I think it is known that everything's just coming from the product of Killing vector field. But in the case of Kerr, you do have something that is irreducible.
So when you make these impositions upon X to get the superrotation, supertranslations, you're saying it basically looks like Minkowski top order. If you instead talked about some like lower level of granularity and made it look like Kerr, like it made a degree all the way up to Kerr order, maybe you could get a Killing-Yano tensor. But if you didn't, I don't see how you would get it. It would just be Minkowski and then it would wash out or something like that. You probably have to have a degree with the metric, like to pretty high order.
Yeah, but super translation, I mean,
Then wouldn't it just be?
Expect in the case of Minkowski, it's really because you go to infinity, right?
Wouldn't actually doing that kill everything except for the Poincare algebra? And then how would you get?
We can again just write down two tensor and
I just don't know if making it agree to even higher order, like with care, for example, making it be care plus some stuff.
Yeah, but then you can put in,
Would that kill the entirety of the algebra at the same time, the vector fields, at the same time as you got the two form? You got the two form, okay.
yeah.
But at the
But
cost.
This two form may not come from those Killing vector fields. You make it something else.
I know you want to get the two form, but if you get the two form, do you accidentally kill all the super translations, for example, by making it agree at such a high level? No, I'm just worried about. I'm saying you're imposing all these extra equations,
Yeah.
making it agree to higher and higher order.
Yeah.
Is that going to reduce the vector algebra to the Poincare algebra
Uh-huh.
at the same time as you pick up a Carter tensor? That would be cool, but you don't want to kill the super translations.
No, you want to keep that.
I know. I'm just not sure if you would.
Those are like a hidden symmetry. You don't. I mean, those don't come from any proof. I mean, like Killing field, they always come from isometric group. So here BMS group come from a BMS algebra come from BMS group, but there may be some symmetry only at the algebra level, just like this Killing tensor. That's what I meant.
A symmetry only at algebra level that doesn't okay, yeah, maybe.
Like this Carter tensor. I mean,
Yeah. Yeah, I can't think of a straightforward way to integrate that. They get a diffeomorphism or something. Okay, sorry for not going to time. I apologize.
Okay, yeah.